Hi guys, I wanted to just take a minute to talk about this big scary thing, the normal curve, right? The normal distribution. I thought that maybe I should go over this because it seems like a lot of people are really struggling with this idea, and I think it's because you want it to just kind of be magical, you know, like you did back in geometry and algebra 2, where you just kind of follow the same process every time and it always works. Well, you know, math isn't exactly like that. We are trying to recognize how this is like what we've done before and apply those ideas, but math is more about ideas and logical processes. So what I want to do in this video is not work through a bunch of problems, because we've done a lot of those, and if we still haven't got it, then maybe that's not the problem. I thought maybe we should just kind of look through and talk about the normal distribution curve and what that means. Okay, so the first thing that I'm going to bring up is what's called the standard normal distribution. All right. Now, the standard normal distribution curve has this bell curve that you are so familiar with. All right. So, there we go. No, it keeps pushing the button. Okay, let's try this again. There we go. All right. So there's your bell curve, more or less, right? Now, the idea is that something that has a normal distribution, the data accumulates towards the middle, right? And we talked about how this is something like heights. You know, people, the average height, there's a lot of people that are close to the average height right here in the middle, whereas you know, there are other people that are, there's very few people that are really, really tall and very few people that are really, really short. So it's kind of normally distributed. A lot of things kind of fit into this category, but none of those are the standard normal distribution curve. Okay, those all have normal distribution. The standard normal distribution curve is kind of like the parent function, right? Back when we did transformations, the first thing we talked about is we said, okay, we've got these parent functions. For example, y equals x squared, right? There's this parent function that is so simple, you can draw it in your sleep. But then from this, you could add things, you can multiply, you can divide, and that changed the shape of this parent curve, right? It could move it over to the side so that your vertex was no longer at 0, it was somewhere else. It could stretch it out so it was a little bit wider, but it still has the basic parabola form. And if you zoomed out, it would look exactly the same as the other one, just in a different position. Okay, it's the same idea with the standard normal distribution. A standard normal distribution has its center, its average, at 0. And not only that, but the standard deviation, by definition, the standard deviation of that is 1. Okay? Now, the other thing that's interesting is if you were to take this curve and add up all of the area, like if you were just to say make little boxes and find the area of those little boxes and add them all together, the total area for a standard normal distribution would be 1. And that's why if the whole area is 1 or 1.00, that's 100%. And that's how this now ties into probability. We say, okay, well, there's 100% probability of being under this curve somewhere. And so now we break it down and they found patterns. They said, okay, well, within one standard deviation, there is a 68% probability. Now, how did that probability come about? Well, it's because they measured the area under this curve. And so the area inside of there was 0.68 units, right? The whole thing was 1, and this part was 0.68. So what's the probability of being in that area? Well, it's 0.68 out of 1, or 0.68, 68%. Okay, now remember that's just a rule of thumb. You should use your calculator to get the actual number if you're having to do this on an exam. And so we're starting to kind of get the idea of this parent function. Now, the neat thing is with this parent function of the standard normal distribution is that we can use these values to find out the probability. Your calculator can do that for you. Okay, and what it will do is you can put in any value, not just one standard deviation, but you can put in something else. Let's say 1.5 1.5 standard deviations. So if you want something that's 1.5 standard deviations away from maybe the center, so let's say we want to know the probability of being in this area from 0 up to 1.5. Well, you can use your calculator for that. Now, the function you use on your calculator is the NormalCDF. Now, what that means, I want you to know what those letters means. That's the normal, the standard normal distribution, cumulative distribution function. So there's the distribution. The function is because it's a function, it's a curve, and cumulative means that it's adding up lots of pieces. What it's doing is it's adding up all the little boxes inside of whatever area you want. Now, when you do the normal CDF on your calculator, it asks for a lower bound, it asks for an upper bound, it asks for the average, the mean, and it asks for the standard deviation. Now, if we're working with this, with the standard normal distribution, the parent function, then your mean is 0, your standard deviation is 1, and then your lower and upper bounds are whatever you want to bound on this picture here. And so if I wanted from 0 to 1.5, then that's what I would put in. I would go from 0 to 1.5. Now, we have a special name for these values, and that name is the z-score. The z-score is just how many standard deviations are we from the middle, which on a standard normal curve is equivalent to the distance from the middle, right? Because one standard deviation is a distance of 1 from the middle. 1.5 standard deviations is a distance of 1.5 from the middle. So we're starting to starting to get an idea of what this stuff really means. The z-score is just how many standard deviations are you away from the middle. Now, if I wanted this to be within 1.5 standard deviations, I'd need to go the other direction as well to bound it by 1.5 on both sides. Okay? Now, what this gives you, if you put in the normal CDF, the result will be a probability, or a percentage, or a proportion, right? That's what it gives you, because it's telling you how much of the curve is this area from 0 to 1.5, how much is covered. What is the shaded area there? That's what's coming out. Now, the only reason you would ever use the other function we learned about on the calculator, that's the inverse norm, well, that's just the opposite of this one, right? The inverse norm asks for the area. It asks for the mean, and it asks for the standard deviation. If I'm dealing with the standard normal distribution with this average of 0 and the standard deviation of 1, then all I need is the probability, right? And I'll put in whatever my area is, and it will be from that value down, right? The inverse norm just gives me the area from a specific value, how much of the curve is beneath that, right? So if I put in, for example, 0.60, then it would give me 60% of the area starting at the bottom. So it would be all of this, because that's 50%, plus a little bit more to get up to 60%. And so it would give me whatever value is right here. Now, I know I'm starting to make a mess of my standard normal distribution, but hopefully you get that idea. If I put in 0.40, it would give me up to about this point right here, right? It would be telling me what is this value for which 40% is below that. Okay? And so hopefully you're starting to get an idea of how this works. Now, we haven't even started looking at specific examples yet, because that understanding, that basic understanding, is the important part. Now, if you want to put it with any other bell curve, that's just a transformation of this standard normal distribution. So if I now put it with any other bell curve, let's say that I'm talking about, I think there was a question about speed limits, right? And they said the average speed is 40 miles per hour, right? So that's our center now. Obviously, it's been shifted over. Just like this quadratic was shifted over to the side, this has been shifted over from where it used to be at an average of 0. It's been shifted over. Maybe my standard deviation now is 10, right? Which means, just like the quadratic here, this quadratic used to have a certain width. If I stretch it out, it's a little bit wider now. It still has the same ideas, the same basic proportions and pieces as the parent function did. It just has some different values and looks a little different. So now if I make my standard deviation 10, then it's going to have the same general shape, but I now have some different values. So again, if I want a probability, I'm going to use the same function. Anytime that you want to get a probability or a percentage or a proportion, you have to use the normal CDF, because that is the cumulative function that adds up all the little pieces between our boundaries. Okay? And if I want to find a specific value, then I have to have an area for it so that I can find out the area. So like if I wanted to know, what speed are 25% of the cars going slower than, right? The first quartile. What is the maximum speed of the first quartile? The first quartile is the first 25% of cars. And so if I wanted to know what speed was the fastest of that first quartile, I need to find out where the 25% takes place. So I go until I find 25%. Okay? And that 25% area will give me a specific value right here, which is what the inverse normal will give me. Okay? So it's important that to understand the big picture, that you understand the little picture of the standard normal distribution. And I hope that this video was able to help put some of those things into perspective and help you understand kind of the basics of what's going on behind the scenes when we're looking at the standard normal distribution and we're looking at these other distribution curves. Remember that if we're dealing with the standard normal distribution, then these values are just the number of standard deviations, or the z-scores. Okay? If I'm dealing with actual data, with actual numbers, then generally speaking, the lower and upper are going to be lower and upper values, which means I'm going to need the real mean and the real standard deviation. It's the same down here. If I put in 0 for the mean and 1 for the standard deviation, it's going to give me the z-score. If I put in the real mean and the real standard deviation, then it's going to give me the actual value for which that area is beneath that number. Okay? So I hope that is helpful, and if you have any other questions, please feel free to come and ask me, or just send me an email. Ciao.